Hello again, and welcome to another episode of Quantum on the Treadmill. Like always, these are questions I ask AI as I try to learn the mysteries of quantum. I hope you enjoy this episode. Thanks again. I'm John Willis, also known as Bocciagalupe. The birth of quantum, how Max Planck solved the ultraviolet catastrophe. Most scientific revolutions begin with someone trying to overthrow the existing order. The quantum revolution began differently. Max Planck was not a rebel. He was not trying to destroy classical physics or replace it with a strange new picture of reality. In fact, Planck deeply respected the established laws of physics. His goal was to solve a relatively narrow technical problem involving the color of hot objects. Instead, he introduced an idea so radical that physics would never be the same. That is why many historians identify December 14th, 1900, the day Planck formally presented his radiation law, as the birthday of quantum physics. The problem hiding inside a hot object. To understand what Planck accomplished, we have to begin with something ordinary. Objects change color when they are heated. A metal bar placed in a furnace first begins to glow dull red. As it gets hotter, it becomes orange, then yellow, and eventually almost white. The hotter the object becomes, the more energy it radiates, and the more its glow shifts toward higher frequencies. Physicists wanted to describe this process mathematically. To simplify the problem, they imagined an ideal object called a black body. A black body absorbs all electromagnetic radiation that strikes it. When heated, it also emits radiation in a predictable pattern determined only by its temperature. Scientists could approximate a black body using a hollow metal cavity with a small opening. Radiation entering the hole would bounce around inside and be almost completely absorbed. When the cavity was heated, radiation escaped through the small opening, allowing researchers to measure how much energy appeared at different frequencies. The experimental results formed a smooth curve. At lower frequencies, the energy increased. It reached a peak and then declined at higher frequencies. The experiments were clear. The theory was not the ultraviolet catastrophe. Using classical physics, scientists developed an equation known as the Rayleigh-Jeans law. It worked reasonably well at lower frequencies. But when the equation was extended toward higher frequencies, especially the ultraviolet region, it predicted that the amount of emitted energy should grow without limit. According to the mathematics, a heated object should release an infinite amount of energy at high frequencies. That obviously did not happen. A furnace did not flood the universe with deadly ultraviolet radiation. A warm fireplace did not vaporize everyone standing nearby. The experimental curve rose, peaked, and then fell. The classical prediction rose forever. This failure became known as the ultraviolet catastrophe. The catastrophe was not a physical explosion, it was a catastrophe for the theory. Classical physics, which had successfully explained motion, gravity, heat, electricity, and magnetism, appeared unable to explain the radiation coming from a simple heated cavity. Something was wrong. Enter Max Planck. Max Carl Ernst Ludwig Planck was born in Kiel, Germany in 1858. He came from an academic family. His father was a professor of law, and several other relatives had been scholars, theologians, or government officials. Planck was musically gifted and played piano, organ, and cello. He reportedly considered pursuing music professionally before choosing physics. That choice was not necessarily encouraged. When the young Planck told a professor that he wanted to study theoretical physics, he was warned that physics was nearly complete. The great discoveries, he was told, had already been made. There were only a few details left to clean up, but it may rank among the worst career advice in scientific history. Planck studied at the universities of Munich and Berlin, where he attended lectures by major figures such as Hermann von Helmholtz and Gustav Kirchhoff. He became particularly interested in thermodynamics, the study of heat, energy, and entropy. By the late 1890s, Planck was a respected professor in Berlin. He was not known as a scientific revolutionary. He believed strongly in order, continuity, and universal physical laws. This makes what happened next even more remarkable. Planck's desperate assumption. Planck was trying to find an equation that matched the measured blackbody radiation curve, and he eventually discovered a formula that fit the experimental data extremely well. But finding an equation was not enough. Planck wanted to derive it from fundamental physical principles. To do that, he turned to the statistical ideas of Ludwig Boltzmann. Planck imagined the walls of the blackbody cavity as containing tiny oscillators. These oscillators absorbed and emitted electromagnetic radiation. Classical physics assumed that the oscillators could exchange any amount of energy whatsoever. Energy was believed to flow continuously, like water being poured from one container into another. Planck tried something different. He assumed that energy could be emitted or absorbed only in discrete portions, and these portions came in amounts determined by the frequency E equals h nu. Here, E is the energy of one portion, nu, the Greek letter nu, is the frequency of the radiation, and h is a new constant of nature that became known as Planck's constant. The total energy could therefore appear only in whole number multiples, E equals n h nu. The number n could be 0, 1, 2, 3, and so on. An oscillator could possess one energy unit, 2 units, or 3 units, but not 1.47 units or 2.63 units. Energy, in Planck's calculation, came in packages. Planck called these packages energy elements. The word quantum, from the Latin word for how much, would later become the name for one such discrete amount, a staircase instead of a ramp. The difference between classical physics and Planck's idea can be pictured as the difference between a ramp and a staircase. On a ramp, you can stand at any height. The possible positions form a continuous range. On a staircase, you can stand on the first step, the second step, or the third step. You cannot stand halfway between steps unless there is another step there. Classical physics treated energy like a ramp. Planck treated it like a staircase. The size of each step depended on the frequency. Low-frequency radiation had small energy steps. High-frequency radiation had much larger steps. This solved the ultraviolet catastrophe. At low frequencies, the energy steps were small, so the behavior looked almost continuous and classical physics worked reasonably well. At high frequencies, however, each energy packet required much more energy. At ordinary temperatures, it became increasingly unlikely that an oscillator would have enough energy to produce those large packets. The amount of radiation therefore declined at high frequencies instead of increasing toward infinity. The catastrophe disappeared. Did Planck understand what he had done? Not completely. Planck initially regarded quantization as a mathematical device, a way to make the calculation work. He did not immediately claim that nature itself was fundamentally composed of discrete packets of energy. He later described the assumption as an act of desperation. That phrase captures the moment perfectly. Planck had tried to preserve as much of classical physics as possible, but the experimental evidence forced him to introduce something that classical physics could not explain. His solution worked, but its meaning remained uncertain. Was energy truly quantized, or was quantization merely a mathematical trick used when counting possible arrangements of energy? Planck had opened the door without fully stepping through it. Einstein takes the quantum seriously. 5 years later, Albert Einstein pushed Planck's idea much further. In explaining the photoelectric effect, Einstein proposed that light itself behaved as if it consisted of localized packets of energy. These packets would eventually be called photons. Planck had quantized the exchange of energy between matter and radiation. Einstein suggested that the radiation itself was quantized. Planck was initially uncomfortable with Einstein's interpretation. Like many physicists, he remained committed to the idea that light was fundamentally a continuous wave. But the quantum idea could not be contained. Niels Bohr would use quantized energy levels to explain the structure of the atom. Louis de Broglie would propose that particles such as electrons could behave like waves. Werner Heisenberg and Erwin Schrödinger would build entirely new forms of mechanics. Max Born would interpret the wave function in terms of probability. The quantum staircase Planck introduced into one radiation problem gradually became part of a new description of reality. Why this is considered the birth of quantum physics. There were earlier clues that classical physics was incomplete. Scientists had studied atomic spectra, thermodynamics, electricity, and the strange behavior of light. But Planck's work introduced the central idea that gives quantum theory its name. Certain physical quantities do not vary continuously. They come in discrete amounts. On December 14, 1900, Planck presented his derivation to the German Physical Society. That date is widely treated as the symbolic beginning of quantum physics. The revolution did not arrive all at once. Planck did not announce that classical physics was dead. There was no immediate agreement about what the quantum meant. The full theory would take another quarter century to develop, but the first crack had appeared. Physics could no longer assume that nature always changed smoothly. The tragedy behind the scientists. Planck's professional life brought enormous recognition. He received the 1918 Nobel Prize in Physics for his discovery of energy quanta and became one of Germany's most respected scientists. His personal life, however, was marked by extraordinary tragedy. His first wife, Marie, died in 1909. One of his sons was killed during World War I. Both of his daughters died following complications from childbirth. Another son, Erwin, became involved in resistance to Adolf Hitler and was executed by the Nazi regime in 1945. Planck remained in Germany through both world wars. He attempted to preserve German science under increasingly brutal political conditions, sometimes confronting Nazi officials while also making compromises that remain the subject of historical debate. His home was destroyed during an Allied bombing raid, taking with it many of his papers and possessions. Planck died in 1947 at the age of 89. The scientific institution, now known as the Max Planck Society, was named in his honor. It remains one of the world's leading research organizations. The reluctant revolutionary. What makes Planck such a fascinating starting point for the quantum story is that he did not set out to create quantum physics. He was trying to solve a problem. The experiment showed one thing. Classical theory predicted another. Planck could have dismissed the mismatch, questioned the measurements, or forced the old theory to survive. And instead, he followed the evidence. He introduced energy packets because they made the equation agree with nature, even though he did not fully understand what those packets meant. That may be one of the deepest lessons in the history of science. A revolution does not always begin when someone claims to possess the truth. Sometimes it begins when an honest scientist admits that the old explanation no longer works. Planck solved the ultraviolet catastrophe by turning energy from a continuous ramp into a staircase. That single move prevented an imaginary infinity, explained the black body spectrum, introduced Planck's constant, and gave physics the idea of the quantum. He thought he was repairing a crack in classical physics. Instead, he opened a door into an entirely new universe.